Hi, everyone. In this video, we're going to take a look at trying to use the algebra we've been working with in terms of using exponents and squaring and those order of operations and things like that to do some graphing. And in the meantime, it's to remind us that graphing ultimately is an application of order of operations in which you start with a symbolic representation of something and you end up with a graphical representation, a visual representation. And it just tells you a little bit about the relationship between X and Y, input and output. So we'll start by taking a look at the objectives. We're going to revisit the graphs of nonlinear functions. We kind of give something away there. And I want to remember that f of x equals x squared is just another way of saying y equals x squared. So x is the input. X squared will generate the output. So when you read f of x, it's not f times x. It means the result of the function of x, the output from x, is equal to what you got when you squared x. And then these are just four different forms that we're going to take a quick look at. Big picture, though, we're going to look at how order of operations is going to be a tool in graphing. So every example is going to be graph using an input-output table. So you might notice some patterns developing. You might see other videos where you can come up with a graph just based off of looking at the equation, like we ultimately were able to do with linear equations, but that's not the goal of this video. We're going to create input-output tables. So going back to the old idea of x's go in, y's come out, we'll pick a handful of them and we'll throw them onto the graph, and then we'll see if some patterns developing that we can just assume is going to connect smoothly between the points, because that's how functions typically work. So we'll just start by any old input that you want, and 0 is usually a pretty good one. So plug in 0, we will plug 0 in for x into our equation, we'll square 0, we end up with y equals 0. So that means that if I use x equals 0 as an input, I got y equals 0 as the matching output. A, I should put it in the table. B, I should put it on the graph. So let's see what some other points are going to do to figure out where the graph goes from 0, 0. We can use x equals 1, and we'll speed this up a little bit. Plug in x equals 1, you square it, you get y equals 1. Got the point over there. Next, you could use x equals 2. X equals 2, square it, you get 4. Now that's starting to look a little bit like some pattern is developing, but it doesn't feel like it's linear. You can almost see like well, this was a rise of 1 and a run of 1. This was a rise of 3 and a run of 1. So that's not going to be linear. And you might be tempted to continue going in that direction. You certainly could. But what I want to point out is in graphing expressions that have x squared in it, it's really important that you be a little bit more creative with the inputs. So I'm going to go into this direction then. I'm going to plug negatives in. -3, you square it. Remember carefully that when you square a negative, you get a positive. So a pretty common mistake is to not write the parentheses and to think that your final answer is -9, especially when your calculator plays a hand in that. But squaring -3, you get 9. Squaring -2, you get 4. Squaring -1, you get 1. And what we start seeing then is that the points over here were really telling you only half the story. If we had tried to assume how this pattern was going to continue, you might take you further down here. But it turns out that there's some level of symmetry here. So the key ideas that I want you to think of as you look at that graph are, A, when you're graphing something that has a squared in it, don't expect it to be linear. I already talked about it a little bit, but you can see that there's bigger drops and smaller drops, and the rise over run is not consistent. When we look at it on a table value, we used to see as you went +1, if you went -5 this time, then the next time you went +1, you went -5 also. That was the mark of a linear expression. These aren't linear. This shape that you end up with is called a parabola. It's U-shaped. There's a lot of symmetry to it. And it's going to be key to try to figure out where this vertex is. The vertex is a word that's describing to this bottoming out point right here. And there's other times it ends up being a topping out point. But as you go through this, and that's going to be more of a next course thing, you'll have ways to figure out where that vertex is, which really helps you pick some smart points to see the symmetry. So we're looking at U-shaped graphs when we see x squared, expected to kind of rise during some part of your graph and drop during some part of your graph, and not consistently in a straight line. Okay. So what happens when you get a little bit more creative, or a little more involved? X squared plus c. In other words, x squared with some adjustment at the end. And I say adjustment at the end because I don't want to reinvent the wheel here. If I'm going to create an input-output table for y equals x squared minus 2 in my second example, I'd like to keep in mind that I already had a whole list of x squareds here. So if I kept the exact same x's and I thought of these as the x squareds that came out from our first function. Why don't I just subtract 2 from all of those? So that would leave me with a new output for -3 of 7. And you notice by using the same x value, I ended up with a point that was on the same vertical line here. It was in line with it this way, but because I subtracted 2, it ended up being 2 points lower, 2 units lower. Shift down of 2. I could do the same thing with this point, where this represented x squared when x was -2. But if I want to graph x squared minus 2, I could have the x squared and take the 2 away, and that's going to shift that point down also. So it seems like every single point is just dropping 2, and this is not something that's new. This is something that plenty of people have picked up on before, and it's this first idea of something called transformations, which is when you know that you have an x squared parabola, and you know that your graph is very closely related to it. We start talking about things called a parent function, and then the transformation of the parent function. In this case, the transformation that's signaled in the equation, as soon as you get good at this, is that your x squared, your parabola, got dropped to. Now that might seem a little overwhelming to you right now. So why don't we stick to the idea of order of operations? We could have just created this graph by plugging in 1 and squaring 1 and subtracting 2 from it. And then later on plugging in 2 and then squaring 2 and subtracting 2 from it. So you don't need to be using the idea of transformations to come up with the graphs, but I would like you to be kind of aware that it's out there. And maybe you can start asking yourself some questions about graphs that you get. How were they related to the equation? Because the key ideas are, first of all, input output and order of operations it still runs the show. You can graph any function ever using inputs and outputs. It's tedious. It's not where we want to end up, but it's a great place to start. Number 2, all x squared functions graph as parabolas. That's even if there's a little adjustment like a -2. And then the third thing is there are connections between equations and the details of the parabola. But right now, we're not going to be so concerned in using those. We're just going to kind of keep an eye out and maybe make some mental notes of them. Third one we're going to graph today is y equals x minus 1 squared plus 3. And you might look at that and think, well, that doesn't have an x squared in it. So I maybe do need to start from scratch. So let's do that. We'll use the whole idea of order operations. We'll plug in a 1. Why did I choose to start with 1? Well, there's something to it, but we're not going to talk about why that is right now. When you plug in x equals 1, following the order of operations, which is a good safe way to graph anything, 1 minus 1 would happen first. That gets you 0. Then you have to square the 0, which remains 0. And you add 3, and you come up with 3. So 1 goes in, 3 comes out. That's your point. We can pretend we don't know that this is a parabola and just go right on in and do another point. We can plug in x equals 2, and you get a y value of 4. Now, I want to point out that x equals 2 gives you a y value of 4, but also x equals 0 gets you a y value of 4. You get there 2 different ways because 2 minus 1 got you a positive 1, and 0 minus 1 got you a negative 1. But the squaring here gives you equal results. And that's that idea of symmetry. So I'm going to put both of those in the table. And I'm going to put both of those on the graph, and you can kind of start seeing how things are growing out of this point 1, 3. 1, 3 right now has been this point of symmetry for these other 2 points. And if I plugged in the next x value in this direction, that would be -1. And if I plugged in the next x value in this direction, that would be 3. And when you use both of those x values, again, symmetry takes over. Squaring a positive and a negative gets you the same result. You end up with something that looks like that. So we are getting that parabola again. So even though it's not x that is being squared, it's this more complicated expression, x minus 1 that's being squared, it's still going to lead to symmetry. It's still going to lead to a parabola. And you might start noticing that x equals 1 that I chose as my first point was pretty useful because that made this 0, which was kind of a real special moment. And then everything else, whether this became 1 or -1, it created symmetry. Whether the x minus 1 became 2 or -2, it created symmetry. And that was real intentional. Okay, so that's your original x squared graph. And you can see that there seems to have just been a few transformations again on that thing. It looks like maybe it got shifted up 3. And looking at the equation, you might know why that happened. And it got shifted to the right 1, which is a little surprising. But again, there's kind of some signal about that. Not something we have to worry about right now. You're doing order of operations to graph parabolas. Key ideas: Input, output, and order operations is still running the show. That should be your top goal for this video. Number 2, all x squared functions graph as parabolas. That's a nice tool for when you graph this. If you, it's a good way to check your work. If you're not seeing a U shape, something went wrong. Or maybe you're, if you're seeing something that looks a little more like a line, maybe you're just working on one side of the vertex and you need to identify some points on the other side. And then once again, there are connections between equations and the details of the parabola. The last one for this video is this guy. And now that one really, it has an X term, not just the squared piece, but the X term. So I'll definitely go with input output table, and I'm going to do it very quickly. An example of input output table to come up with this thing would be I could use X equals 0 as an input. I would get 5 as an output. I have my point there. You might be thinking that since in the last problem I intentionally chose this point to build symmetry around, you might be thinking there's symmetry here, but there's not. If you just use order of operations with -1, you would get 0. Order of operations with 1, you get 6. If you look up and down here, actually, I don't see any symmetric point at all. So what I'm going to do instead is I'm going to plot those points. And then I'm going to draw the parabola, which I kind of see it here. It's going to be really tempting to make it top out at 1, 6 because it's the highest point I found. But I can tell that 1, 6 is not a point of symmetry because 1 unit away in this direction or 1 unit away in that direction, I'm getting different things. So it turns out that the parabola looks more like that. So the point of symmetry, we didn't really find it. So that's the one downside to using input-output in order of operations to create a parabola. You don't know for sure that you found the vertex. You don't know for sure that you found this point of symmetry. But if you go into this with these key ideas, 1, use input-output to try to generate points. 2, if the thing you're graphing has an x squared in it, expect it to be U-shaped. And then 3, there's going to be lots of transformations that change the features of a parabola. You notice in this one, it's upside down. There's something about this equation that made that go upside down. The other thing you might not notice is it's a little bit narrower. It's a little bit tighter, or someone could say it's like growing or shrinking faster than x squared did. Again, there's something about this equation that does that. You don't need to know those things right now. So when you do your problem set today, it's going to be some equations. I'm going to ask you to try to graph it, and you should be checking your graph by noticing that it's a U-shaped. And if it's not a U-shaped, go back and check your order of operations, or go check your sign work. Thanks.